Okay, so yeah, so let's just review some knowledge to begin with, stuff that I think you should know. So first off is bounded convergence theorem. Bounded convergence theorem. Can somebody tell me the bounded convergence theorem? And it doesn't matter if you don't know it or not. Have you seen the bounded convergence theorem? Yes. Okay, so here's the idea, right? You have a bunch of functions, right? You have a sequence of functions, S of n, right? And you have, for all of these functions, you have some bound, right? There's some upper and lower bound, right? And then what? What's the rest of it? Under these conditions, if something happens, then something else happens. Just to bring you all out of your Christmas stupor. Does anyone remember? What are the convergence theorems about? What are they about? Switching, yeah. Switching, limit, and integration. Right? When can you switch the order? When is basically right, the limit of the f of n, as n is infinity, equal to the integral of the limit. So, and this will be some function, right? So so the statement is if these guys are bounded and the limit at every point is if there's a pointwise limit to pointwise convergence to some function, then you can change the order of integration. You can then these things commute. Okay. Right? So this is the bounded convergence theorem, and all the convergence theorems are sort of along these lines. Right? Under certain conditions, if you have a certain sort of convergence, then these things commute. You can change the order. The limit of the integrals actually does equal the integral of the limit, the integral of the limit function. Okay. Maybe I won't do all of these things, but monotone convergence theorem. I'm going to just do three or four things to review. Monotone convergence theorem. Okay. Again, you're going to have, of course, some sequence of functions. Right? You have some sequence of functions, right? And does anyone remember the conditions? It's monotone convergence, right? You can sort of guess what's going to happen if you have any yes? Yes, yeah. So typically what uses says increasing, right? If this is an increasing, if this is an increasing sequence of non-negative functions, non-negative measurable functions, and you have right, you have the again, you have a pointwise limit almost everywhere. Then again, you can commute, right? The limit, the integral of the limiting function actually equals the limit of the integrals. Right? So when can you commute limit and integration? Okay. Can anyone give an example of a case where you cannot commute a limit and integration? What goes wrong, right? What goes wrong? Just give a sequence that commutes pointwise to some function, but the limit of the integrals is not the integral of the limit. Sorry, what's your name?
Brian.
Brian. Yes.
N times the characteristic function, or 1 over n times the characteristic function from 0 to n. The interval.
Okay. So yeah. So the integral is always 1, right? The integral Like you're looking at these guys that spread out, right? These guys that spread out. Well, the limit is 0, but the integral is always 1. Right? The limit function, point-wise, the limit function is, the limit is 0 at every point. Right? So here's your f1, here's f2, here's f3, f4, right? And at every point, well, fn of x is going down to 0, right? So the integral of the limit is 0, but the limit of the integrals is 1, right? Because the integral of each guy is 1. Okay. That's that's typically how one explains it. You could also have something like a block that moves to the right. A block that so s of n being say the characteristic function of n plus 1. So at every point the limit is 0, right, but the integral is 1. Right? So it moves. It keeps on walking. It moves to infinity. Okay. The support moves to infinity. Okay. Okay. So last one. Dominated convergence theorem. Last convergence theorems, the dominated convergence theorem. Can anyone say this one? Does anyone remember this one? If you don't, it's okay. You just come back from partying and drinking and whatever you're doing, like carousing.
So sequence of measurable functions.
Yes.
And then you have an L1 function.
Yeah.
And the absolute value of each of the measurable functions is dominated by the L1 function.
That's right. Yeah.
And then the same thing.
Yeah. Okay. So you have some L1 function, right? You have some L1 function g. Okay. So it's an integrable function, right? And what you have is that you have a bunch of other functions, s of n, right? That so you have a bunch of other functions, s of n, right? And they're all these guys at every point dominated by this guy. Okay, so they live inside of this lemma. Okay, this is how it was explained to me when I was an undergraduate. Okay, you have this function. You got all these functions, and as long as they live inside this lemma, right? Because that's what an L1 function is going to look like, right? It has to have some decay, right? Right. So you have a sequence of measurable functions, and you have g, which is integrable, right? G integrable function, right? And then, as usual, right, if the functions, if the sequence converges pointwise to some function, then you have that the integral of the limiting function is the limit of the integrals of those functions. Okay. So these are the three. Well, I mean, this is really the big theorem of the big convergence theorem. And in the notes, I've also included a sort of generalized dominated convergence theorem. So take a look. Okay, everyone all right? Okay. So we're just reviewing, when you can interchange limit and integral, right? And the problem is that you could have these guys that whose supports move off towards infinity, but you see that won't work. If you have this rule of the limit, then those guys don't satisfy that. Right? That's because they leave the limit. Okay. So a couple of other things that will become needed shortly. The notion of absolutely continuous measure. So you have x in measurable space, and you have these two measures mu and nu measures defined on the set of measurable sets. So this is the space, right? This is the space. And this is the sigma algebra of measurable sets. Right? And you've got these two measures defined on this. Okay. This notion of one measure being absolutely continuous with respect to the other. If whenever the measure of the set A is 0, one has that the new measure of A is also 0. We say that nu is absolutely continuous with respect to mu. So absolutely continuous. So, and this notation is the measure, like A is one of those measurable sets, right? You're taking the measure, whenever the measure of a set is 0 with respect to the mu measure, the measure of that set is 0 with respect to the nu measure. Okay. Then we say that nu is absolutely continuous with respect to mu. Okay. The main thing the main result we use with that definition is the so-called Radon-Nikodym theorem. So you have x, f, and mu, a single finite measure space. Okay, and you remember sigma finite means that you can have this collection of sets such that their union is the whole space, and each one has finite measure. Each one has mu finite measure. Okay, so it just means that it just means that X is a countable union of sets which each have finite measure. Okay, so you have a sigma finite measure space, and you have nu, a measure on F, another measure on F. If nu is absolutely continuous with respect to mu, then something good happens. Does anyone know what that good thing is? It's okay if you don't, Brian.
There exists a function such that if one measure is the integral of the function with respect to that measure.
Right. So there exists some sort of like density function. That function is called the Radon-Nikodym derivative. So if you have absolute continuity, then there exists a non-negative measurable function f called the Radon-Nikodym derivative. Derivative of mu with respect to mu, such that for all measurable sets, the nu measure of E is the integral of this function against the mu measure over that set. Okay, and you can see that, right? If mu, if mu is 0 on that set, then of course nu is going to be 0 on that set, right? If the measure of E in the mu measure is 0, well then this integral is 0, right? This integral is 0, and so nu is going to be 0. So that clearly forces the the measure nu to be absolutely continuous. And in fact, this is the only, this is what always happens. Okay, that any absolutely continuous measure is realized in this way, can be realized in this way. Okay. Okay, everyone all right? Don't worry if you've forgotten these things, or if you've forgotten, I'll bring up basically any sort of relevant knowledge that we need when we see it. Everyone all right? Okay, so now let's really get started. Well, we're going from review stuff to sort of basic stuff. So we're not really, I'm sorry, let me take that back, we're not really getting started yet. So now let's go to some basic questions. Okay. So first thing we're going to get to is the important notion of Banach cases. Okay, so just, and you may sort of feel embarrassed, or I feel a little embarrassed to put up this definition, but I'm going to put it up anyway. So if V a vector space over R or C, we call this function going from V to the field. Okay, so let me say over some field F, and really what I mean is R or C. I'm just going to give the definition of a norm. Right? We call this sort of function a norm if it satisfies three qualities, right? A norm. If three things happen, one, that you get 0 only when, if and only if the function, the thing you're taking the norm of is the 0 vector, right? 2, the norm of scaled vector is of course the absolute value of the modulus of the scalar times the norm of the original vector. Right? And then the last one is the most important one. What is it? What's the most important thing for the norm? The triangle equality. Triangle equality, and you have this. So as long as you have these three things, then we call this function a norm, and we call this, and in that case, we call with this norm, just sort of stupidly, we call it a norm vector space. Norm vector space. An obvious definition. Okay. And we've all taken 131, right? So you know what a metric is, right? So remark, as you know, right? Given a norm, it induces a metric on V by the distance between two vectors defined to be the norm of the difference. Okay. So any normed vector space is a metric space. Right? So then once you have a metric space, you have all the theorems that you had, and all the notions that you had back in 131. right? And right, so you have this metric, right? Once you have a metric, you also have, say, for example, notion of open sets, right? You have the notion of open disks, open balls in space, right? You have open sets, interior points, right? You have all the notions of topology, right? As long as you have a norm. Okay. Now, it's not the case, it may be the case, we're not really going to emphasize this. Radon does more of this, but Radon talks more about the cases when you don't have a norm, right? And yet you have a topology also, and you want to talk about convergence and this sort of thing. So we may talk about that as well. But at least not for now. We're not going to. So in that case, in this, you have these things called semi-norms, and you induce a topology from the family of semi-norms. But anyway, at least for now, it's straightforward. You have a norm. The norm induces the metric you use to create the topology. Okay. Right. So in particular, you have the notion of Cauchy sequence, right? And once you have the notion of Cauchy sequence, you can talk about completeness, right? And that brings us to the definition. If the is complete with respect to the induced metric, we call V, like the obvious name would be a complete norm vector space, but instead we call it a product space. At the expense of clarity, we get sort of a cooler name. Okay, so the prototypical examples of Banach spaces are the LP spaces. So the typical examples. LP spaces. Right. So and you have some. Again, you have some sigma finite vector space. You have the space, the underlying space, the collection of measurable sets and the measure, right? And we have this thing called LP space, right? LP x f mu is what? What is LP space? Are you all familiar with this? You don't have to be familiar with this. I'm actually going to talk a lot about it. But I just want to know, have you seen it before? Close your eyes for a second. Okay. Close your eyes for a second. Lift up a finger if you've seen LP spaces before. Okay. Put your fingers down. Okay. Great. Okay. So some of you have and some of you have. That's fine. In fact, those of you who haven't seen it are in the right place because I'm going to talk about it quite a lot for the next day or so. Okay. So LP spaces. Somebody want to tell me what they are? I'm going to have. This will be. For now, it will be P between 0 and infinity. What's the LP space? What's an LP space? It's a simple definition. Are you shy? Eric, tell me what an LP space is.
It's the space of all functions whose you take the integral and you raise the function to that p power and if it converges.
Exactly. So you define this thing. So this LP is the set of all functions, all measurable functions, say complex value, such that the integral of the absolute value of f to the p everything raised to 1 over p is finite. Okay. So of course you don't need this 1 over p, right? Right? If this is finite, then certainly this thing to the 1 over p is finite. The reason I put that in is because we use that to find what's called the LP norm of the function. Okay. So it's a set of all functions for which the LP norm is finite. Okay. Such that the LP norm is finite. Okay, and of course you put the 1 over p in to make sure that you satisfy property 2 of the norms, right? Because otherwise, when you scale the function, right, you'd be multiplying by a epsilon of a to the p, right? So you need to take the square root, take the pth root of that to compensate. Okay. Okay, so this thing is LP space, right? Space LP is a set of all functions such that this integral is finite. Right, so for example, for a simple example, if x is the natural numbers, say, right? So suppose we're looking at sequences. Right? If x is the natural numbers, right, and mu is a counting measure, right, then you have some sequence, right, a sub n, right, you have some sequence a sub n, right, and you have some sequence, and you say that that guy is in LP, right, this thing is in LP. If the sum of the p powers of the moduli is finite, right? And actually, this is normally called little LP. People call this little LP. Okay, so we already noticed that the second property of norms is satisfied is we make it true by putting it as 1 over p. What about the first property? Is it true that when you integrate a function, is it true that the LP norm of the function is 0 if and only if the function is the 0 function? Is that true?
Almost everywhere.
Right, so you need to be almost everywhere. Okay, so it's not true. Okay, so this is actually not a norm. Okay, this is actually not a norm, right? Because you can have a function that is 0 everywhere except for some points, right? So that function is not the 0 function, right? But its norm is 0. Its LP norm is 0. Okay, so we can't really call this a norm. Because right, you could have functions, can't have functions. You could have f, which is equal to 0 almost everywhere, and then the LP norm is 0. Right, then the LP norm is 0. Okay, so what you do to compensate for that is instead of considering the class of functions, you consider the class of equivalent. You consider the set of equivalence classes. Right? You introduce an equivalence relation on the functions by saying, I'm going to consider functions to be equal to each other, to be equivalent to each other, as long as they differ on sets of measure 0. Okay, right? And in that case, you mod out by that relation, and then in that case, a function that's equal to 0 almost everywhere is the 0 function, right? Its equivalence class is the equivalence class of 0. So you just mod out by this relation, and then the first property is true. Okay, so basically you sort of finagle it, and you say, well, really we're going to consider functions to be equal as long as they differ on sets of measure 0. Okay. And that's how you ensure that the first property is true. So really, you're not looking at functions. You're not looking at functions, but you're looking at equivalence classes of functions. But as Stein says, in practice, it does no harm to just think that we're dealing with functions. So typically, you just think we're dealing with functions, and occasionally you may have to remember that you're not really dealing. You're actually dealing with equivalence classes. So one corrects for this by considering equivalence classes of functions that are equal almost everywhere. Okay. So that's one thing that's a little bit problematic. We can't really call this a norm for that reason. And then the second thing, do we know that this satisfies the triangle inequality? Does this satisfy the triangle inequality? Does this satisfy the triangle inequality? So in fact, it's incorrect to call this a norm. In the case P is between 0 and 1, because then the triangle inequality fails. So we actually don't know, first off, we don't know that this satisfies the triangle inequality, and in fact, if we look at it, and you will in your homework, you'll see that for P between 0 and 1, the triangle inequality fails. And so we'll spend the rest of the class actually proving that the triangle inequality holds for the case P greater than or equal to 1. Okay. So it's wrong to call this thing a norm for two reasons. I mean, it's you have to mod out by this equivalence relation. And second, you really shouldn't call it a norm for P between 0 and 1. But people do anyway. People sort of sloppily just say the LP norm. Even if, and you know that it's not right for P less than 1. Okay. So LP spaces, we said that this is actually an example of like the prototypical example of the Banach spaces, but for right now, we don't even know that it's a norm vector space. We need to show two things, that it's actually a norm vector space, and also that it's a complete norm vector space. Okay. And then we can actually say that this is an example, it's a Banach space. So, to show that the triangle inequality is satisfied by this norm for P greater than 1, we'll need to introduce some really useful tools. So we'll introduce some inequalities that are sort of like the common tools of people who do analysis. Okay, tools, and for now it will be to show the triangle inequality. But really, in particular, the first tool we're going to introduce is something that people use all the time, and it's Hilbert's inequality. And this will be really crucial. Like, it's something that really you use like every day of your life. If you're doing research, then like you just use Hilbert's inequality. Like there's no tomorrow. Like depending on your shoes, it's like shoes. Okay, I don't know. Maybe that's not. But anyway, Hilbert's inequality is pretty good. Okay, so to state Hilbert's inequality, we need to introduce some notion. First is the notion of conjugate exponents. conjugate exponents. So you have some p between 1 and infinity. We define for p greater than 1 and p less than infinity, so p between 1 and infinity, we define p prime to be the solution of 1 over p plus 1 over p prime equals 1. That is to say, p prime equals p over p minus 1. Okay. Or that p prime times p minus 1 is 2. However you want to think about it. Okay. So p prime is the number that satisfies this. Of course, you see that if the dual of p is p prime, then the dual of p prime. I'm sorry, this is also called the dual exponent. You see that the dual of p prime is p, right? P prime prime is of course p. And for p equals 1, we define p prime to be infinity and vice versa. Right? And that sort of makes sense, right? If you're thinking about this, if p is 1, then you want p prime to be infinity. If p is infinity, you want p prime to be infinity. Okay, so these are the dual exponents, and why they're called dual to each other will become clear when we talk about dual spaces. Okay, so here's the theorem, L is an equality. So 1 between p and infinity, and it will actually be true for the limit for the n cases as well, but we're just going to state it this way for now. Because we haven't defined p infinity. If f is in LP and g is in LP prime, then in fact the product is in L1. These guys from LP spaces of dual exponents, then the product is in L1, and in fact the L1 norm is controlled by the product of the LP norm of f against the LP prime norm g. Okay, so also true for the endpoints later. It'll be trivially true in the endpoint case once we define L infinity. Okay, so the key to this will be the key lemma. The key lemma will be the following, which is sort of, if you've read the text, you know that this is sort of a generalized arithmetic geometric inequality. So here it is. If a and b are non-negative numbers, and theta is some number between 0 and 1, then a to the theta, b to the 1 minus theta is dominated by theta a plus 1 minus theta b. So it's some sort of averaging statement, right? If you take theta to be a half, then this says that the product of the square roots is dominated by the average, right? Dominated by the arithmetic average, right? The geometric average is dominated by the arithmetic average. Okay. So So, so I can do this. Okay, so the proof goes like this. So the first thing is that you reduce it. You say, well, without loss of generality, you can assume that B is non-zero, right? Because if B is non-zero, then it's sort of, and if B is equal to 0, then it's obviously true, right? Because you get 0 on the left-hand side. Right? So assume that B is non-zero. And then you do a reduction, okay? And you say, well, actually, we notice that it suffices to show that for all a bigger than or equal to 0, that a to the theta is less than to the theta a plus 1 minus theta. So we can reduce this we can make this reduction. As long as we're in the case B is not equal to 0, all you need to do is show this is true for all A. Okay, and the reason is, of course, for if we have that, we're given that, apply it to A over B. Right. Apply it to A over B. What you get, of course, is right, A to the theta B to the negative theta is less than or equal to theta A B minus 1 plus 1 minus theta. Right? And then you multiply through by B. Right? Multiply through by B, and you get the inequality that you wanted. So all we need to do is prove this simpler statement. Right. And this simpler statement is proven using calculus. Okay. So to prove something called a star, so if we're given, once you're given star, that gives you the original statement. To prove star, just consider the function f of theta equals x over theta minus theta x plus 1 minus theta, right? And show it is less than or equal to 0. Okay. So this is just a calculus problem. It's really a calculus 1 problem. You take the derivative, you find where its maximum is attained. Its maximum is attained at a point where it's 0. Okay, so that's it. So this is proven by calculus. For us, so just keep this thing. So, we're going to use this. This is a tool. We've got this generalized arithmetic geometric inequality. Right? We're going to use it in the case. So for example, let p equal to 1 over. I'm sorry. Let theta equal 1 over p. Right? Then of course, then 1 minus theta is 1 over p prime. Right? Because that's 1 over p plus 1 over p prime is 1, right? And so the statement is that a to the 1 over p, b to the 1 over p prime is less than or equal to 1 over p a plus 1 over p prime b. Right? Or more cleanly for us, let's substitute these guys with their p, with a to the 1 over, take everybody, teach each of these guys to the p power, and you get ab is less than or equal to 1 over p a to the p plus 1 over p prime b to the p prime. that we'll use to get Halber's inequality. So, everyone all right? Moni, you look a little unhappy. Are you, is there anything wrong? No? Okay. Everyone okay?
Just to make sure.
Yeah, yeah.
Just to make sure.
Yeah.
F of theta equals x to the theta.
Yes. Ooh, wait a second. What is that? F of x, sorry. Thank you.
Or f of x.
Yeah.
X to the theta minus.
Yeah.
Theta.
It's theta x plus 1 minus theta. Okay. So thank you. It was wrong. Good. Okay. Okay. So, so let's get the proof of Halber's inequality. So now proof of Halber's inequality. Okay. So remember that the statement is that the LP norm of the product, right? If you have these guys in spaces that are with dual conjugates, then the product is in L1 and the product is in L1 and their L1 norm is controlled in this way. In the text, they use Q instead of P prime. It's okay. I will probably mess up and call it Q or sort of use them interchangeably. If I look at my notes right now, I see that I'm using Q. So. So again, we do a reduction. So we reduce the problem. We say, well, without loss of generality, we can assume that these things are non-zero, that the LP norms, LP and LP prime norms are non-zero. Right? Because if they were zero, that would mean that the functions were equal to zero almost everywhere, in which case we'd be asking is 0 less than or equal to 0, which is of course true. Because if the LP norm is equal to 0, that means the function is 0 almost everywhere. Okay. So, in that case, you divide, or rather, you replace f by f divided by its LP norm and g divided by its LP prime norm. Right. And you see that this reduces the problem that it suffices to show that that this is less than or equal to 1 for all functions whose LP norm is 1 and LP prime norm of this guy is equal to 1. Okay. So you do a reduction. Right, again, you say, well, look, if it's not equal to 1, then just consider the function that you get by normalizing by its norm, like by dividing by its norm, and apply this thing to it. Oh, you get the previous thing. So this is the consequence. Again, this is the consequence of that. Okay. So we just have, all we have to do is show that this is true when the LP norm of F is 1 and the LQ norm of G is 1. The LP prime norm is 2, but G is 1. Okay. Okay. So so we will use exactly this thing to get a pointwise inequality. So we say, well, look, we know that, well, by the lemma, we have that f g is bounded by 1 over p f to p plus 1 over p prime g to p prime, right? That's what we're saying here. This thing. you get the L1 norm. You get the L1 norm of FG. Right? Integrating the left side, you get the L1 norm of F times G. And on the right hand side, right, you get 1 over P times, well, you get the LP norm of this thing to the P power. Right? You get the LP norm of F to the P power plus 1 over P prime times the LP prime norm to the P prime power. Right? Because you're missing the 1 over P prime. Right? You're missing the 1 over P prime, so you get the norm to the P power. Okay? Right? But these are 1. Right? These are 1, and you get 1 over P plus 1 over P prime, which is 1. So that's the proof. Right? That proves the reduced statement, and from the reduced statement you get the full statement of Eller's theorem. Eller's inequality. Okay. So that we still haven't gotten that we have a norm, right? Our goal right now is to show that that the LP norm actually is a norm for P greater than 1. We haven't gotten it yet because we need to get that the LP norm is a triangle, satisfies the triangle inequality, which is called Minkowski's inequality. We'll use Helder's inequality to get Minkowski's inequality. Okay. And then from there, we'll have a normal vector space, and then we'll show that it's actually a complete normal vector space, and then this will actually be a Banach space. Okay. And then we'll do even more interesting things. Okay, that's it for today, unless there are any questions. Oh, yeah, please pass over your sheets of information about yourselves to the right and forwards. Yes, I'll post the notes on Sakan. Yes, those of you who are not registered for the course, send me your emails or something. I should ask for your emails on those sheets of information. But just send me a mail or something. Send me a mail and I'll send you the notes. Okay. I hope you're excited for this course. It should be pretty fun. Analysis is sort of like a lot of small facts, cleverly chosen. Like no one step is hard, right? Every step is pretty straightforward, right? But how did you know to choose those steps, right? That's the hard thing, right? So but don't be just think it's all just all very simple steps, but which ones to make? Okay. See you next time.